clustering pattern, and you wonder, if you look at the correlation functions, or perhaps to the power spectrum description, perhaps I can recognize some signatures of the underlying quantitative structure. So that's what we will first look at, and we will find some good news on the use of these functions, but also some interesting observations showing that these things are not good at all if we want to understand the complexity of the cosmic web. Now, if you're interested in this field, it's a vast field. There was a standard work that I can certainly recommend to all students who would be interested in starting work and research in this field. It's a sort of the basic book, textbook on the field, which is already more than 15 years old and was written by Vicente Martinez and Hussar. And that book you can still obtain from, for example, Amazon. And it's basically a collection, a discussion of the various means of statistical analysis of the distribution of galaxies, distribution of mass, etc. However, it's 15 years ago, and in the meantime, a lot of things happened, in particular with the cosmic web, and that you won't find in this book. We will cover some of it in this lecture. Now, the first important thing to point out and to realize is that what we see in the universe, in the observations, is a realization of a stochastic process. It's not a fixed thing, it's just if you were taking a certain cosmological model, for example, as we saw with structure formation, the cold dark matter model, then you can ask yourself what kind of structures form. Well, it's never a fixed structure, it's actually a statistical realization of an underlying stochastic process. The stochastic process can be extremely complex. It can be somewhat simpler, and actually we saw that the cosmic microwave background is a Gaussian field, and that actually, statistically speaking, is about the most simple statistic that we know of, that we can fully describe analytically. Most of the time we cannot. But we're stuck with our universe, because we only have one universe, one realization. So that actually is a problem, right? If you would have, for example, a Gaussian distribution, of human heights, right? That's approximately a Gaussian distribution. That is a Gaussian distribution for males and a Gaussian distribution for females, with a slight shift in the mean. And you would want to determine the properties of this distribution, and you take one specimen, you, and you say, that's it. Well, you clearly see that's a difference. So neither of you are very representative of this distribution. You would need a lot of people, at least all the people in this room, the men and the women, to get at least kind of an impression of what the distribution is. But of the universe, we only have one. So we have a problem, right? If you want to decide on the underlying process, what to do with this one realization. That's realization of the universe as a whole, but also in terms of structures. We are saved by the fact that it looks like we can use the Ergodic Theorem. That means that the universe is so vast, so large, and the stochastic process that is underlying the structure that we observe is of a smaller scale than the overall universe, and that means that there are enough statistically independent volumes in our observational universe, such that you can use the different regions, statistically different regions, to sort of get an idea of the underlying statistical distribution. That saves us. Otherwise, as cosmologists, we would be in a hopeless situation. Actually, on the largest scales, when you look at the cosmic microwave background, perhaps you saw yesterday the spectrum, And if you look well, you see that as you go to larger and larger angular scales, there is a band of uncertainty around it that widens and widens, simply because you have less and less and less of those realizations. So you become more and more uncertain of what the real mean is, right? But overall, for the study of the cosmic web, we are safe. The cosmic web is around, at most, a couple of hundred megaparsecs. Most of it is less. It's a few megaparsecs up to 100. And there are many, many volumes of that in the observational universe, so we can use that. But always keep it in the back of your mind, right? The cosmological certainty. Why doesn't it move? Oh, it seems the battery of this thing is out. Okay, then we do this. Now, yesterday, we already heard from Vicent that, and he introduced the two-point correlation function. So we learned all about it. And the two-point correlation function is basically telling you, you know, what's the difference between these 6 panels? And you clearly see what's the difference. This looks much more uniform than that one. That means if you would have a uniform distribution and you would take a little volume here and a little volume there, and they would be a distance r, and you wonder how many pairs are there between these volumes, then of course it's the mean number density squared times the volumes of the little volumes, like that, right? That would be your average. But if it's clustered, and here you clearly see that there is clustering, if you are sitting in this volume, and on average you start counting, then you have many, many more pairs at that clustering distance r than you would expect in a random distribution. And it's all encapsulated into this function psi r, the two-point correlation function that was introduced by Totsuyi in Kihara and then by Jim Peebles. We heard the story all about that yesterday. So, would this not be enough? Well, you already see for the cosmic web it can't be enough because there is only one distance. It's completely isotropic. And in the cosmic web we're describing something that is anisotropic. So certainly that might be a problem. But there's also another problem. It only looks at the distribution between 2 regions. But actually, when you would, for example, have a structure that is a wall, and you would sit in the wall here and take another region there, then, you know, you can't see the difference between sitting in a wall or in a cloud. You would need 3 points at least. Here in the wall, and outside of the wall, before you start to see, hey, there's a difference here and a difference there from what you see over there. So that's clearly that this is not the whole thing. The two-point correlation function is not a complete description. Actually, in statistical physics, they know this very well. If you look at the distribution of particles in a volume, you actually need the whole hierarchy of not only the two-point correlation function, but the 3-point, 4-point, 5-point, up till the endpoint. Well, if anyone knows how the 1001-point correlation function is correlated to the presence of filaments, they may come forward and tell me, because I would be most interested. I don't have a clue even what a 4-point or a 5-point correlation function. I somewhere read that actually the human eye, and I can't find the paper anymore, but I read it at one go, the human eye is capable of seeing the 4-point correlation function, but not anymore the 5-point correlation function. So you could have 2 distributions that have the same 1-point, 2-point, 3-point, 4-point, and then a different 5-point. And we wouldn't see the difference. I read it somewhere, and then I can't find the reference anymore. So since 10 years I'm looking for the reference, I can't find it. But it's very interesting that the human brain apparently isn't doing that. Now, what the 2-point correlation function in practice seems to do is a very nice behavior. At small distances, it behaves like a power law. It means it is an expression of a self-similar scale. Must be related to this hierarchical distribution where different scales are sort of manifestations of the same underlying process, and the process is gravitational clustering. This seems to be pretty universal behavior, and that was already found by Peebles, Totsuyi, and Kehara, and here you see how extremely strong this is, in the sense that every time people look at different catalogs, samples of galaxies, they always find this gamma is 1.8 and a scale R0 of 5 megaparsecs. Like Vicente pointed out yesterday, cosmologists have made a mistake to call that correlation length. And then if you walk down the street to your colleagues of statistical physics, then at first there is a complete misunderstanding, because they would never call this correlation length. They would call this at best a clustering length. It's an amplitude. It has nothing to do with a characteristic length. And that led to a lot of misunderstanding up to way into the 90s. One of our Italian colleagues played here a substantial role, I would mention in that. Actually, here you see what would be a more proper thing if you would log plot of the correlation function. Then here it would be a power law, and the amplitude is R0. I would call that clustering length. But if you would put it linear, in this case, this is a hypothetical situation, in this distribution, which is sort of web-like, you would go somewhere through 0, and then it goes up again. This thing is what is more the coherence length and what statistical physicists would call correlation length, right? And that actually says something about the cosmic web. If you would have a web-like structure, this scale tells you approximately the size of the voids. Okay? So, now, the two-point correlation function actually is extremely important, because it is a second-order statistic. For the initial distribution of mass, which we saw is a Gaussian distribution, so the primordial distribution, that indeed is the entire story. Gaussian fields means that the 2-point, the second-order moment, is everything there is to know. The third-order moment and all the higher-order moments are either 0 or dependent on the second-order moment. So that's the story. That means that the two-point correlation function indeed is very interesting and important. It is also the Fourier transform of the power spectrum. We heard about that yesterday. And so both of them are different sides from the same medal. You look at the same thing. It's a second-order description of the underlying mass distribution. It also goes into the nonlinear stage of gravitational clustering, where it becomes very interesting. You can actually write down the equations of motion for the first stages of the development of structure, and sort of get the nth order moments, etc., of this density field distribution, and you will find that always the two-point correlation function shows up. So indeed, it is very important. But perhaps, I think the most important fact about the two-point correlation function is that it is the strongest argument for the fact that the universe obeys the cosmological principle. The fact that the universe is isotropic and homogeneous. Isotropic is not too difficult, because the cosmic microwave background is the ultimate proof that the universe is isotropic in every direction. But how do we know it's homogeneous? We don't have spaceship Star Trek, the enterprise like Star Trek that we can go to another part of the universe and see whether the circumstances there are the same, right? We can't. So how do we know for sure? It's the basis of cosmology. And still, it seems we cannot prove it. Actually, we can. And the simple thing is this. We can not only look at the two-point correlation function in space, but we can do it much simpler. We can look at the sky. Then we don't have to determine distances, but we just look at the pairs of galaxies on the sky. So you take an image or a map, like the Million Galaxies survey map, and you look at the sky, and actually what turns out to be is that that two-point correlation function, W theta, the angular two-point correlation function, excess of pairs on the sky, is a projection of the spatial two-point correlation function. That's expressed by a very famous equation, Limbus equation, right? So why would that be interesting? Now, if you look at it in detail, you find the following. That projection depends on the amount of galaxies that are projected on the sky. If you look deeper into the universe, you have more galaxies on the sky. You go to a fainter limit, right? If you go to a fainter limit, what happens? Well, here you see the result. This is the APM survey. We saw that in the past few days too. And this is the correlation function for different magnitudes, limits of the, magnitude bands of the galaxies. And what do you see? The two-point correlation function of the brightest band of galaxies has a higher amplitude than the ones of the faintest ones. Moreover, if you look well, you see that the scale at which they cut off is, for the brighter galaxies further away, a larger angular scale than these ones. In all cases, this is indeed, on that side, the small angular size, is indeed a power law. Theta 0 over theta, and gamma here is 0.8. That's 1.8 minus 1, because it's a projection. But what about this behavior? Now, think about it. Why would that be? Well, actually, when we are looking out in the universe, and now we know, we look through the cosmic web, and we see filaments and voids, but there is no indication that there are voids larger than 100 megaparsecs. There's a spectrum of sizes, but there are no 500 megaparsec voids. If there were, we would have a problem with the cosmological principle. Imagine that you have these huge holes. That means that the universe on very large scales would not be homogeneous. What would happen in that case? Well, let's first have a look when this is not the case. So the largest structures are the ones that we see, a couple of dozen up to 100 megaparsecs. When you then look out in the sky, then when you take only the brightest galaxies, that means that comparatively you only take the galaxies that are nearby, right? Except for the very brightest exceptional one that you see far away, most of them are nearby. So actually you're looking at the cosmic web nearby. That means you're actually probing structures that is sort of defined by the voids nearby. So those voids, 50 megaparsecs, have a large angular size, right? The structure also involves less galaxies, so you still have sort of the spatial structure to see the spatial variations. So actually the clustering of the nearby galaxies is expected to be more substantial. So you expect two things. The clustering should have a higher amplitude, and it should go out to larger angular scales. Now you probe deeper and deeper into the universe, and imagine there are no larger structures. Then what you are actually projecting is galaxies from more and more layers that are also embedded in the cosmic web, but it's the cosmic web further away. So the same void of 50 megaparsecs is smaller. So you start to actually project smaller stuff that actually intrinsically, spatially, is from the same thing, but in angle, it's smaller. So it starts to dilute the signal to smaller scales. And also the amplitude becomes less because you're projecting more and more and more randomly scattered galaxies on top of each other. So actually this behavior seems to be suggesting that indeed there is a limit to the amount of structure that we see in the universe. Imagine there would be a large 500 megaparsec void that still would have this huge size on the sky, and that would suggest it would remain over there, but there's no indication for that. It even allows us, by using the Limber equation, and, I don't have it here. Sorry. It seems that the most beautiful one seems to be skipped out. Probably had it thing. Actually, it turns out that when you use the Limber equation, you can actually rescale all these two-point correlation functions according to the depth of your survey, characteristic depth. And they all project totally on top of each other. Totally in accordance with the fact that there are no larger structures in the universe. First of all, it shows sort of a characteristic scale for the cosmic web. And secondly, it proves there are limits to the amount of structure that we have in the universe. And indeed, on the very largest scales, the universe is pretty homogeneous. Right? This is, in my view, the clinching argument for the cosmological principle. Another manifestation of what we will see the cosmic web is when we look at the two-point correlation function, but, and also Vicent mentioned that yesterday, you don't look only as a function of one particular scale, but you split it off in terms of the transverse scale on the sky and the depth, basically the redshift. And you basically count now pairs in redshift sky distribution volumes, and you therefore make a two-dimensional correlation function. This is a two-dimensional correlation function, and you see it looks like an onion, right? Now, what is the color basically means, the intensity is actually the amplitude of the two-point correlation function. So when you would actually take this line, that's the sky line, and you would sort of take this section, then you would very nicely get this power law behavior. But you see, it's totally anisotropic. When you look compare this line versus that line, there is a substantial difference. So does that mean that the universe is anisotropic? Well, I just said that I believed in the cosmological principle, so that's hard to believe. The explanation is actually very straightforward. On 2 days ago, I pointed out the finger of God, you know, the clusters and the galaxies in the clusters, and the galaxies rushing through these clusters with huge velocities of around 1,000 kilometers per second, right? Now, what would happen is that actually, as a result, you saw these lines, these edges that are clusters. So on average, along the line of sight, you get a stretching of the two-point correlation function of the clustering. And you get these reflections of these fingers. As interesting is that when you look, it's not only the finger of God, it's actually also, if this would be the spherical isotropic one, and it's, you see, it's not only not in the center, not isotropic, but neither on the outside. There it's flattened instead of stretched. Why would that be? Well, we also saw yesterday that because of the formation of structure, we have huge migration streams. Matter starts to displace from the original position, is moving through the universe, has its own velocity. It's moving in particular towards the filaments and the walls. So actually, on average, if you look in the sky, you see that galaxies are moving towards the filaments and towards the walls. And statistically speaking, that means actually in this direction, it gets compressed when you look in terms of redshift. And that's what you see here. So this is a direct manifestation of the existence of these large structures in the cosmic web. And it's a direct manifestation of the dynamics. It's even so beautiful and powerful, these diagrams, that actually the flattening you can immediately relate to the amplitude of the velocities involved with the migration streams on large scales. And that immediately depends on the amount of dark matter in the universe and on the dark energy content and character in the universe, in particular when you probe it at different redshifts. And nowadays it's considered to be one of the prime probes of dark energy. It's one of the Euclid key projects to determine this at different redshifts. And on the size of the flattening, that tells you how fast matter is moving in the universe, and that's an immediate reflection of the underlying dark matter and dark energy. So yeah, in the end, maybe the correlation function is interesting and powerful to describe the cosmic web. Too bad it's not. Here you have an example. What you see here is a distribution, a very simple toy distribution, where the mass is actually contained in filaments and walls. It's a geometric model, right? It's a density field. So you would say, well, okay, I'm going to describe this by the two-point correlation function. So you determine the two-point correlation function of this, and you get something interesting. Now, you do something that I explain further on too. You say, okay, but I can actually decompose this into the density field into its Fourier components. And the Fourier components have an amplitude and a phase. I will come to that slightly later on. A Gaussian field has a random, pure, uniform, random distribution of phases. Right? So the game you can play is the following. You take this distribution, you take its Fourier transform, you take the amplitudes, you keep the amplitudes of the Fourier transforms, but you randomize the phases. That would be basically a Gaussian field. But the power spectrum would not change, because the power spectrum, and therefore the two-point correlation function, which is its Fourier transform, remains exactly the same because it looks at the amplitude. It doesn't look at the phases. So the power spectrum of this distribution and the two-point correlation function of that distribution is exactly the same as that one. To accept this as a very good description of the two-point correlation function of this structure or not, but I would say I lost a lot of information here. Right? So, out two-point correlation function. It's not very informative for these complex geometric structures that we just saw as the cosmic web. It has some information about scales, it has some information about amplitude, but it can't possibly say anything about the connectivity, shapes, etc. of the underlying structure. So, too bad. Let me shortly point out to you the companion of the two-point correlation function, the power spectrum. So that's actually already what I remarked yesterday. The power spectrum we heard yesterday was used for the BAOs too, and it's in fact the same as the two-point correlation function, because they are each other's Fourier transform. Right? So this is basically the definition of the power spectrum It's the ensemble average of the amplitudes, of the quadratic amplitudes of the density field, right? It's the ensemble average, but on average, you can, with the Ergodic Theorem, you can determine this by looking at different volumes. That's the definition, right? Now, it is the Fourier transform of the two-point correlation function, so they both have the same information intrinsically. It's just that for some practical purposes, for some samples, it's better to use the power spectrum, has more information, lower errors, or for some others, it's the two-point correlation function, right? So the power spectrum has the same information. It is powerful because it could, for example, determine the scales of the baryonic acoustic oscillations. But here comes this argument of where it may not provide us with the information that we always want to have. This was this argument of the density field being the Fourier transform of the Fourier components of the density field. Well, the Fourier transform, Fk, is actually a complex number. So it has a real part and an imaginary part, Fr and Fik. You can write that as the amplitude, Fk, times e to the phase, theta k. Right? So that's what I meant with phase. So the power spectrum, if you look right here at the definition, it's basically the product of these things. Well, if you multiply this with its complex conjugate, the only thing you get is actually the quadratic of the amplitudes. The phases, e to the I theta, e to the minus I theta, disappears. It's not in the power spectrum. Right? So, you might say, well, I don't know what the phase is, so forget about it. That's good, isn't it? Well, let me show you a very nice example that was made by Peter Coles I think already 15 years ago, and I think it's a beautiful illustration of the difference of where the power spectrum is not informing us. So imagine the following. We take a map of planet Earth, the surface of planet Earth. So you see clearly the oceans, you see the continents, right? So let's take another map. Let's take W map, distribution on the sky of the cosmic microwave background. We know that's a Gaussian field. So there the phases are non-existent, or they are uniformly distributed. It's a random distribution. So let's now do the following. You take the map of planet Earth, you take the Fourier transform, or the spherical harmonic, and you take out the phases and replace them with the phases of W map. What would you get? Then you do the reverse game. You keep the phases, but you replace the amplitudes with the amplitudes from W map. So what would you see? What would you guess? And it's really nice to see what happens. This is planet Earth with the amplitudes given from the map of planet Earth, but with the phases of W map, cosmic microwave background. Now, if you see any remainder of the continents, you may tell me, but I don't see anything. Right? So let's do the reverse. This is the amplitudes of the cosmic microwave background, but with the phases of Earth, of surface Earth. So, you know, the heights and the depths of the oceans and the heights of the mountains, yeah, they have a little bit of a problem. But you can see the outline of the continents. You can draw it very accurately. So actually, if you look at this, it's clear the phases have much more information about the structure, the geometric outline of the structure that you see on the surface of Earth, than the amplitudes. So I don't think I need much more arguments to convince you that the power spectrum is a nice tool, is informative for certain aspects, but not for describing complex structures. Right? So we need to do something else. Now, in view of the time, I'm going to skip this for a moment. This is I should have... I wanted actually to address here the situation that we have to translate the galaxy distribution or the particle distribution in embodied simulations from which we infer the cosmic web. That's a discrete distribution, while we're always talking about basically continuous fields. So you have to translate these things. And if you want to learn about the cosmic web, you have to do that in a way that keeps actually the geometry of the underlying distribution. And what astronomers regularly do is they apply filters. They smooth it with some Gaussian filter or whatever, but that actually destroys what you're looking for, that destroys the signal, and that's not the way you should do. But there are now techniques, and that's this DTFV thing, you can read about it in the notes, that actually keeps all this signal from voids and films. The point is, we will use this further on. Now, the field of following the cosmic web, the kind of structure that we're after, has been really booming, becoming much richer over the past 10 years. And by now, there's a whole slew of formalisms that seek to describe different aspects of the cosmic web that address the complexity of the structure. And just to give you an example, and this comes from a paper that we just published, it's called Tracing the Cosmic Web. Noam Libeskind is the first author, I'm the second one of this, in which we basically assembled a large number of the different techniques that are around now to analyze the cosmic web, and we compare the various aspects that these techniques can do. As usual with such a comparison test, we're not allowed to say anywhere that this one is obviously better than the other one, although I'm absolutely convinced that our own method is much better than any of the others. But that's something else. Now, to set that aside, here you see the classes of methods. So this is not all the methods. We can actually recognize and classify the methods themselves in different classes. Each of them using different, in particular, mathematical and geometric methods to try to deal with this complexity of structure. The first one is the oldest one. That was already started in the 1980s when people for the first time saw in surveys, you know, filaments and those kind of things. And it's what we call graph and percolation techniques. You basically take the dots of the galaxy distribution and you start to connect them in such a way that it sort of is hoped to follow the structures that are probed by these little points. The one outstanding example is the minimal spanning tree. I won't explain here in detail what it is, but it's a very well-known method. It's related to issues like the traveling salesman problem. I don't know whether any of you know the traveling salesman problem, but if you have a salesman who has to visit, 120 towns to sell something, and the towns are scattered over the country, what's the route that he or she should optimally drive such that the amount of gasoline used is minimal, right? So the shortest route connecting all these towns. That's actually not a trivial problem. There's a vast number of papers written about this in the computer literature, and actually one of the algorithms that's used for this, the minimal spanning tree, has been used originally by several people, Suketu Bhavsar, John Barrow, and some others in the 1980s, and actually it's still being used at the moment. For example, the gamma redshift survey of galaxy evolution is actually using a new algorithm based on a minimal spanning tree to follow the cosmic web. So that's class number one, right? A sort of graph. There is also another class of methods, stochastic methods. They are methods that are basically using the following idea. They say, well, you see these filaments, or walls, you could do whatever. Those are actually randomly scattered geometric structures. In other words, it is a bunch of little lines like this, and they are scattered like this. Randomly, that's a very interesting problem from stochastic geometry. It's around for a long time, for 200 years. This is known as Buffon's needle, actually. But here, the process is not randomly, it's done in a certain way that we want to sort of understand. It's clear that the process of the filaments connecting is not determined by itself. It is random, but it is random in a stochastic in a stochastic way, with a non-trivial stochastic distribution. In particular, Elmo Temple from Estonia, in collaboration with Radu Stoica, have been working very hard on this, and they've been writing a very sophisticated, very computationally demanding method called the Bezout sampling method, in which they use Bayesian sampling to finally position lines in such a way that it actually reflects the underlying distribution of filaments. And then they say, this is the distribution that we have, and now we can measure the properties of the cosmic web. So that's certainly a very interesting and promising method. The largest class of methods that is around is the one of geometric Hessian-based methods. It's a mixed bag of methods that actually invokes most of the physics that we discussed already of the cosmic web, the various different aspects. What it simply does is looking at the local geometry. The local geometry of either the density field, or the local geometry of the velocity field, or the local geometry of the tidal gravitational field. And how do you do that? You basically look at the Hessian of the field. So the Hessian of the potential, or the Hessian of the velocity potential, or the Hessian of the density field. Because that's locally probing the local flattening of the matter distribution, or the local deformation of the matters from the matter streams, and etc. So there's a range of methods developed, and they're now competing with each other. One of them is VWeb. That's the method that is propagated by Yehuda Hoffman and Noam Libeskind. And there they actually look at the shear of the velocity field. I will show you some of the results, and some of them are extremely beautiful, of tracing the cosmic web. So it immediately relates to the dynamics. Another method is TWeb, where you don't look at the velocity or to the velocity potential, but you look at the gravitational potential. So you look at the gravitational force and the signature, the anisotropy of the gravitational force locally. And then you trace the web like this. There is another subclass of this, because one of the aspects of this is they have to smooth the mass distribution velocity field on a certain scale. They don't have a multi-scale formalism, so they always assume a certain scale. And that we saw is a bit tricky, right? Because what's the scale that you want to look at? They usually look at something like 5 megaparsecs, but you may argue that that's not the most characteristic scale, which we saw is true because we have a spectrum of scales. Now there is another range of scales around, scale space, multi-scale, Hessian-based methods. of which the multiscale morphology filter, or it's also called Nexus, is the prime example. And I will explain it because I've been very much involved in its development. Two of my former students, Miguel Aragon Calvo and Marius Cotin, have been doing most of the work over here, and they've been developing a very, very elaborate and sophisticated machinery where you don't only look at space as it is, but you also look in so-called scale space, where you look at all scales at the same time. So it's actually sensitive to the multiscale nature of the cosmic web or the web-like distribution. A fourth large class of methods says, I'm not going to look at the geometry, but I'm going to look at the topology. And that, of course, relates directly to the connectivity. If you have two voids, why are they two voids? Well, that's because there is a plane in between. That topologically means something. Either two voids are connected and then it's one void, or they separated and then there is something in between. And actually there is there's a huge field of mathematics called Morse theory, called after the American mathematician Morse, that is actually describing this in detail on the basis of also the gradient and the second order gradient of a field. And the various connectivities between them are actually depending on the singularities that you subsequently can identify. Because on the basis of this information, you can determine the minima. And you can define the maxima. The maxima, of course, are the clusters. The minima are the depths of the voids. But what about the walls and the filaments? Well, they are the saddles. If you are going to walk in the mountains for your holidays, and you go from one mountain to another mountain, how do you get there? You always go through a saddle, and you call it a pass, a mountain pass, isn't it? If you have two valleys, and you want to go from one valley to the other one, you go up the hill, and you pass the pass, and you go down again. What's a pass? A pass is a saddle point. And that establishes the connectivity of the structure. Now, that immediately relates to the topology of the structure. And this has been invoked by a range of methods. One of the first ones that in this field was around is the watershed method that was actually oriented towards defining the valleys in this thing. And how could you distinguish void from void? Well, that's because there's a pass in between. That's why this is an individual void and that one. If the pass would not be there, it would be one void. Right? Now, a very elaborate and sophisticated method for using the same identity, but then for filaments, was made by Thierry Sousby from Paris, and it's called Disperse. It's a machinery you can even download from the web. So that's one of the topological methods. And then there's another one in which I was also involved with Miguel Aragon, and it's called SpineWeb, and it does the same, almost the same thing, but then based on the watershed transform. So that's the topological methods. And then there's the final method, number 5, which yesterday we saw in the meantime is also a large class of methods, and that's phase space. That is trying to look at the multi-stream behavior of the matter distribution. And nowadays we can do that. That was the development I told you about. So you are not only looking at the spatial distribution in X, Y, and Z coordinates, but you can also follow whether there are certain streams that are crossing each other. And we saw that, when 3 streams you see at a certain position 3 streams. You know, I'm in a wall. Because something came from here, something over there, and there is something in between that sort of collided. When it's 5 times, it has gone in this way and that way, that's a filament. And you can use that. You can actually go and use the multi-stream character of the mass distribution to say, well, that's a filament and that's a wall. And there you have 1,000 streams, so that must be a cluster node, because there the thing starts to virialize, etc., etc. Of course, the disadvantage of that approach, something similar if VWeb has the same problem, is usually we don't have the velocities of the structures. We can only have the positions of the galaxies in the observational reality. So this is something that we can use in n-body simulations, right? Now, one of the latest examples in this, and I was referee of this paper and I was incredibly impressed, it was a paper by Florent Leclerc, I already mentioned it to you, where he actually took the galaxy distribution in Sloan, using a sophisticated Bayesian reconstruction technique. He managed to reconstruct the initial conditions that actually had produced this structure. And because he had the initial field, he also knew the potential, and therefore he also knew the velocities, and therefore he had full phase space. And therefore he could use the phase space methods to classify the cosmic web in the observational reality. And I consider that as one of the most promising and potentially rich developments of the coming years, in particular with the large surveys coming up, right? So this whole field is now full of very interesting developments. Now, as you noticed, nearly all of these methods go along with mathematics and computer methods. No longer can we, I'm talking about myself, as astronomers, think that our astronomy knowledge is sufficient and our knowledge of filtering and stuff like that is sufficient. We really have to go to the other side of the street, in my case, to talk with my mathematics colleagues and talk with my computer science colleagues and ask them, you know, do you have methods for this? I learned everything about Morse theory and algebraic topology from the people on the other side of the street. And my astronomy colleagues thought, what the heck is he doing? And this, you know, what is this about? Betting numbers and algebraic topological groups, what's that? But actually we can use it. That turns out to be the case. So for the young people here, always keep open your eyes to other fields. Because there's very rich applications coming from the merging, the synergy between different fields. And you see it over here. Now, let me just pass along a couple of these methods, and so that you get an impression of the method. So the first method I want to discuss is the method in which we put ourselves a lot of work over the past, more than 10 years. 2007 was the first publication. That's the Nexus multi-scale morphology filter that we have actually used to identify the cosmic web and the various components of the cosmic web in simulations, but also in the Sloan and 2DF galaxy distribution. It's actually very interesting. We learned this from medical research, medical visualization. That's where it came from. I remember that one morning Miguel came into my office and he said, I've been yesterday to the hospital and the university hospital. I said, oh, you have a problem? He said, no, I went to talk with a colleague over there who has some very interesting visualization techniques. And he said they have to follow it. When they have pictures, CT scans or X-ray pictures, well, these medical doctors are dealing with it a lot. But they don't have time to study hundreds of photos a day. and see, is there something suspicious over here or not? Well, the first thing is, when you see such a photo, you see these lines. It's arteries, right? Well, we all know that quite often when there is a lump there, then it might not be good news, right? So you want to alert the medical doctor. And of course, he or she would get tired doing thousands of pictures. So what you actually want is an automated machinery flagging a photo and say to the medical doctor, you better have a look over here. So that's where this is coming from. So they look at these pictures, and these visualization people, and I must mention Florak and Kuiper and Sato, who published papers about this in '97. That's where it emanated from. They found a technique to look at these pictures and actually find the arteries, find membranes, find lumps automatically, given the fact, and it's the same problem as the cosmic web, that it is a branching structure. So you have structure on all kinds of scales. So what they do is, what they actually do is construct a scale space. And you see here the Sloan Digital Sky Survey in scale space. What we simply do is we take the density field. This is actually the density field coming from that DTFE technique. So we translate the galaxy distribution into a continuous field. And then we filter it on a whole range of scales. So this is the most refined scales, and here you only see the largest structures. Okay? So what do you do next? Well, the next thing is you're going to determine at each different scale the geometry locally. So when you look, for example, at this, and this is actually taken from Valencia, from the Calatrava Museum of Art. If you were ever there in Valencia, you should visit this architectural miracle. It's beautiful. And you see, all this structure. And it's the same photo, and here you see small lines, filaments, but here you only see the largest pillars, right? So how do you go about it? Well, locally, structure is described by a Hessian. Like this. If you look at the density field locally, you can actually develop the density field into second order, into the density value at a certain point, then the first order, and then the second order is actually describing the shape of the density field. So what we then subsequently do of all these maps, so here we have filtering, is we are going to look here to the Hessian. So this is the second order development, the second order moment, right? So this is the Hessian, which is basically the second order gradient of the density field. And we do this on each scale. And subsequently, we determine the eigenvalues of this Hessian. What does that mean? If you have locally a flattened structure, then actually the eigenvalues tell you the principal axis flattening of the local geometry and the direction. That's the eigenvectors. Now we are interested in the eigenvalues, and at each location, in each of these maps at different scales, we determine locally, does this thing have two long axes and one short one? Or two short ones and one long one? Or two short ones? Or three long ones? So, first case is a wall, locally. Second is a filament. The other one is a node, etc. And we determine then at each scale, at each position, whether locally it's flattened, elongated, compressed, or expanded. And subsequently, we go through the whole set. So that's what you see here, flattened, elongated, a ball, like this. So that's what you do. But then we have all these scales. And we say, well, imagine you are sitting on a large scale in a filament. Then on the smaller scale, you are also sitting in a filament. Probably. Or in a clump. So you have to decide which scale is dominant here. When you're living in a large filament, that might be the dominant signal. So you actually use a criterion, they call that filter bank, and we got the filter banks from these medical visualization people that process these eigenvalues at each location and decide I'm actually sitting in a dominant structure at a scale of 10 megaparsecs here. You're sitting here in a filament. Further out in the field, you may find that you're sitting in a small wall at a scale of 1 megaparsecs. So in the end, we can mark every position in space locally with either living in a filament or living in a wall or a small wall or a large filament or a clump and all these things. So we can actually, on the basis of this scale space maps, get a complete overview of the structures that we see in this volume. So what do we get? Now here you see a map of a simulation, and in the map you actually see what will be the end result. This is what we call the blobs, the lumps. That's where the clusters are. This stuff is basically identified as filaments, but as yet not compressed. Sorry, it's different around. These are the walls. I did it wrongly. These are the walls, and these are the filaments. Right? So that's not the whole story. Because that's not the whole story. Because here there might be lumps, but you're not certain whether they are really collapsed lumps. What do I mean? Well, something can only be a cluster if gravitationally it has collapsed. So what we didn't bring in yet is the absolute value of the density. So that's what we do here. Then we take this set of positions and we determine locally which of these lumps actually passed the limit for gravitational collapse. And then we say, that's a cluster. We do the same thing with filaments and walls, but there the criterion is a bit more elaborate. There we have to determine whether it is not just a one-spot filament, but whether it's actually connecting up to other filaments, and at what threshold that happens in terms of density. So that's another of these threshold criteria, and Marius worked them all out, so it's all dependent on a so-called signature, which is just a tossing up of the various eigenvalues that basically determines the strength of the flattening or the elongation, etc. And on the basis of that, we decide whether something is a filament or not. Right. So at the end, you get this. Here you see the map, and you see here, actually in red, the lumps. In blue, you see the filaments, and greenish starts to be more membrane-like. And you see you get a very nice connection between all the structures of this multi-scale morphology filter, or as we baptized it in the end, this specific technique is called nexus. The color here is dependent on the scale. Sorry, this is all filaments. The red ones is the ones on the larger scales. They are the ones connecting to clusters. The blue ones are the smallest ones, and they are tenuous filaments, and the green ones are scaled in between. Right? So I showed you already this thing. This is where it's coming from. So when we take this point distribution that we saw over here, then here you get the filaments, and in red, orange, you get the membranes. identified via this multi-scale morphology filter. Basically predicated on the local signature of the density field. But Nexus is not only isolated or only dependent on the density field. We actually have 6 different versions of Nexus. Because you can do the same thing for example, the velocity field. You look at the velocity flow on the different scales, the velocity potential, and you determine what the dominant signal in the velocity potential is, or in the gravitational potential, or in the divergence of the velocity field, or in the shear of the velocity field. So what you get here is basically from the same volume, the filaments found on the basis of different physical criteria. So this is our preferred method, Nexus Plus, that looks at the logarithm of the density field. The logarithm is because there is a multi-scale hierarchy, and that in general leads to a power law behavior, and that's why we often, and that's what you often see in maps of the density field, it's the logarithm of the density field. But we can also look at the shear, the velocity shear, and you see that you find the same structure, but only the large guys, the large filaments, because they dominate the dynamics of the large-scale universe. So by looking at the velocity shear, you pick out the largest filaments. And so the combination of the various criteria, it makes this into a very extensive machinery for studying the cosmic web. We could do the same for walls. So that's what's depicted over here. So this is on the basis of the velocity shear, and this is on the basis of the density field. Right? On the basis of that, we can study things like this, and the properties. So this picture that I started with almost on Monday, is actually the Nexus identified filaments. And you see the intricacy of the structure that it is able to find. Right? So, on the basis of that, we can, for example, identify and classify filaments. You find different sort of behaving filaments. You have very long stretched ones that often are found in between the clumps. You have small arteries that emanate from these large-scale filaments. So you can now do the same game as is often done for other astrophysical objects, sort of take your sample of filaments and go around and see, how do they look like? Are there different classes of filaments? How do they percolate through space? Right? How do they connect up? We can do that. You can look into characteristics, like I showed over here. We discussed this already, the density distribution and all this stuff. These diagrams were obtained by Nexus. You can look at the density distribution along filaments. So here you see the density value along a couple of those filaments. This is the density along the filaments, and you see the variation. They're not a homogeneous class of objects, and they are not homogeneous objects. You see that within the filaments there's large variations in density, because there are clumps in there, all these kinds of things. They also are not objects of the same diameter. We saw that clearly with the thick filaments, and you had tiny, tenuous ones. Well, here you see the diameters. These are the tiny ones. Mm-hmm. This is the big guys, right? This is a filament with diameter of 5 megaparsecs. That's the big guy that was in that thing. So we can actually look at distribution functions of filaments and walls. And as I said at the beginning of this lecture, can we quantify the population of this cosmic web such that you can use it for other purposes like cosmology? Well, here, this is quantification, right? Like richness of clusters, but now in a different means. So density profiles we can do too. So that's our method. There are other methods around, and I told you about the other methods something like a quarter of an hour ago. I described various other methods. Now, let me discuss one method that is also impressing me very much, and that recently has produced some beautiful work concerning the observational reality. And that's the so-called VWEB method by Yehuda Hoffman and Noam Libeskind. What they do is actually look not at the density distribution, but look at the velocity distribution. Now on Monday I had wanted to talk about that, but time eluded me. One aspect of the galaxy distribution is not only their location, but also their velocity. We heard that we ourselves are moving with 627 kilometers per second with respect to the universe, simply because we are moving in the cosmic web. We are taking part in a migration. The difficulty is determining this velocity, because it's the velocity that's superimposed on the expansion of the universe, the Hubble expansion, h times r plus v peculiar, and that gave, the sum of it gave part to the redshift. Now, if you ever want to determine that peculiar velocity, you have to determine the redshift and a distance independent of the distance. Right? That's the challenge. And that's the reason why the development in this field has been very, very slow. And for a long time, since 1999, that there was a time in the late 1980s and 1990s that this was a very active field where people tried to make samples, catalogs of peculiar velocities of galaxies in the local universe. And then they gave up because the errors were huge. 10 to 20% is the best you can get for individual galaxies. Because you have to go to these galaxies and determine their distances on the basis of all kinds of distance indicators. And we heard in previous lectures, Elena talked about it, that this is very cumbersome to do. Still, some people are courageous, and they do. And it leads to beautiful insights, because we saw that the build-up of structure is going along with migration flows. And actually, we are actively participating in the migration flows. Now, yesterday in my talk on dynamics, I told you that the gravitational acceleration is proportional to the integral over the density perturbations weighted by 1 over r squared. Right? Now, on these very large scales, there is one extremely nice fact, and that is that the induced velocity by this gravitational acceleration is still very close to its original linear realization. That is, the gravitational field that is going along with this inhomogeneity only managed to slightly move us. We saw that with Seldovich. Only in the nodes, in the high density clusters, where the matter has fallen in, they have been mixed around as the cluster was virializing. This velocity is no longer an indication of the peculiar acceleration that induced this motion. But on the very largest scales, overall in the cosmic web, that velocity is very much in the direction and totally directly proportional to the gravitational acceleration. So imagine this totally opposite to us here in the solar system, right? Because in the solar system, Earth is circling the sun, and the gravitational acceleration is perpendicular to the velocity. Here, it's totally along. And actually, you can write down that this peculiar velocity is exactly the same as the peculiar gravity. It's the integral over the same thing. So if you were to measure the peculiar velocity in our local universe, you could actually make a map of the density distribution and the density distribution of the dark matter. So people did that, but it's cumbersome. Now here you see actually a map that is coming from early 2000s. It's coming from a catalog called PSCZ, which is a near-infrared catalog. And on the basis of that, they managed to infer the peculiar velocities. They didn't directly measure them, but because they sampled the galaxies properly all over the sky, they could basically map in our local universe the flow. And what you see is here in the center is us, and here is the Shapley concentration, and this is what's called the great attractor. And what you see is that we are moving along with an enormous flow in that direction. That's actually why we are moving with respect to the cosmic microwave background. When you look on our doorstep, you see underdense regions, the blue regions here, and when you focus in, you see what's happening in the voids, streaming out. And we see it in reality. The voids are emptying, simply because they lack gravity, gravitational force. So this is already a reality. In the early 1980s, this led to efforts of mapping these peculiar velocities, and this is one of the first systematic surveys, the Mark III one. And what they managed is, here you see basically what they managed. They could measure the peculiar velocity along the line of sight, and it either moves away from you or towards you. It's very inhomogeneous, but when you process it in a proper way, you can translate this into a velocity potential, and that you could convert via that integral that I showed you on the previous page into a density field. And at the time, there was a huge industry and a lot of publicity to the fact that it turned out that we were moving towards something that we could not see. It was called the Great Attractor. And it turned out that the Great Attractor was, unluckily, standing in the plane of the galaxy. And the plane of our own galaxy was obscuring our view on this Great Attractor. It was indeed identified as a massive cluster on our doorstep. And that's where it is. It's a mountain over here. You could almost say it was the second time in human history in which a major object in our backyard was identified on the basis of the gravitational field that was inferred after the discovery of Neptune, which was found in the same way, right? There was a disturbance in the orbit of Uranus that led to the prediction of planet Neptune, and sure, it was there. Here was the same with the Great Attractor. Now, the Great Attractor is only a minor component now of the whole story, as we will see. This would be what we expect of the cosmic web. And you see that the cosmic web signature is, in the velocity field, is far more complex. So here you see flow out of voids, and here is a filament. And you see along the filament there is very complex flow, but if you look well, it's moving along lines like this. If you know your hydrodynamics or fluid mechanics, you see there is a lot of shear flow with on top of that some disturbances due to local peaks in the mass distribution, and they are causing slight inflows, divergences. So do we have any hope of really going in so much detail in the velocity field that we can see in the local universe? Here is a rendering. I showed you the adhesion model. Well, the adhesion model here we used on our local universe, and you see here a rendering of the structure of our local universe. And indeed you see that there is beautiful voids in our local universe, and you see streaming out. But if you would look right at the arrows, you see here beautiful so-called shear patterns. So apparently the cosmic web is going along with shearing motion along the filaments and the walls. The question is, can we take those peculiar velocities and reconstruct that field so well that we can identify the shear in the flow? Let me, in view of the time, go a little bit faster. Well, we can. By the way, small aside, are these motions real, caused by these large-scale structures? Here is a beautiful example obtained by Brent Tully, who's really one of the main players, if not the main player in this field. He determined of two galaxies in the meantime, in the local void, or on the edge of the local void, their peculiar velocity to great accuracy. And you know what? The over-densities in our universe couldn't explain their motion. Not only do we see this large cavity, called the local void, we feel the push. You feel it pushing on this galaxy. You feel the outward push, and it's no less than 260 kilometers per second. Some very well-known colleagues in this field, one of the principal colleagues, once told me as an innocent young PhD student or postdoc that voids were up to nothing and completely useless and totally uninteresting. So I would ask him now, do you still think the same? I think Guido knows who this is. He was even my boss at some point. Now, how do we go about? Now here you see not the velocity vectors, but the so-called streamlines. You know, when you in the evening look at the weather forecast on the news, you don't get the velocity vectors of the moving atmosphere, you get the streamlines, right? That gives you an impression how things are flowing. Well, this is streamlines in a simulation. And what do you see? You see here a complete divergent flow out of the voids. But what do you see here? Here you see the filaments. And this pattern is shear. That's what shear is about. The elements, mass elements, get basically deformed like this. And that's actually what the VWAP method is about. They say we look actually at the divergence of the flows. Because when I look at this divergence, you have a few possibilities. If you have a wall, you actually have a divergence which makes things compress in this direction, what you see here, but then along the other directions it expands. With a filament, it's 2 times along that direction and expansion along 1. It's the same thing. You take actually the shear tensor and you determine the shear eigenvalues, and you do the same thing as what the Nexus did with the density field. You look at the signature. And then you say, well, that's motion along a filament, that's motion along a wall, etc., etc. So this is basically the definition of the divergence. That means expansion or contraction. And this is this deformation described by the velocity divergence. So shear. Divergence is this. I mean, the Hubble flow is nothing else than a huge divergent flow, positive divergent flow. It basically means, are you expanding or are you contracting? But on top of that, you have the component that deforms things. And we saw that already from Zeldovich. The deformation is actually described by the shear. That's by this part of the gradient of the velocity field. And that's a tensor, and you can actually completely diagonalize it and actually determine the eigenvalues of the shear field. So this is a clear divergent flow along 3 directions. This is what the filament is. Inflow along 2 directions, so negative, negative, and positive, like this. And this is what's a wall. Inflow 1 direction, compression the other one. Let me skip this because in view of the time, I want to show the result that recently the group around Yehuda Hoffman and Brent Tullycott, they actually made a new catalog called Cosmic Flows 2. And in the meantime of peculiar velocities, they expanded it to a new one called Cosmic Flows 3. It's the largest catalog of galaxy motions in our local universe. Out to around 100 megaparsecs, they can probe this thing. Now, the Cosmic Flows 3 goes even further, 150. So on the basis of that, they actually were able to reconstruct the velocity flows. And what you see in the local universe, this is us, sitting at the void, and you see we're moving out a little bit like here, and we're moving towards Virgo, and together we are going towards another supercluster. This is real. This is migration in the local universe. Right? You can actually look at this and say, well, what's the velocity potential? And then you can play this same watershed game that we played with the density field to identify voids. But here you can turn it around and say, I'm going to identify the basins in the gravitational potential. They are the bound structures. And they actually found that when you look in the velocity flow direction in the pattern in the local universe, then there is the great attractor. And look at this beautiful visualization by Pomerade, who is part of this group. You really see the stuff moving in like this. And you see that the Milky Way is just part of the large migration flow like that. You can pick up movies from this thing. When you looked at that watershed pattern, it actually looks like our local supercluster and all the structures that we know, like Virgo being an arm of a larger thing, with a void in between, and the Piscis-Perseus arm that we discussed before, are all part of a gravitationally bound structure known as Laniakea. The new address, our new hypercluster in which we live. Now, and this is the concluding thing, recently they had a paper out, which is absolutely beautiful, in which they had Cosmic Flows 3, and Cosmic Flows 3 allows you now to have the velocity field so well that you can actually look at the shear and identify the parts where you have compression along two directions or one direction, and say this is a sheet, or this is a filament, or this is a thing. And this is what you get. So this is the Shapley concentration, massive concentration of dozens of clusters. And you see how much stuff in the local universe is moving up there. This is the Coma cluster. And look in this arm of the Coma cluster. There is this beautiful shear in this whole thing. So this is a beautiful rendering of the identification of the cosmic web on the basis of the cosmic flows in the local universe, right? So we can now not only do this theoretically and in simulations, you can actually apply it to real data. And I think I will leave it here, but perhaps, if okay, the movie should be here. Let me see. For those of you who are, I'm not sure whether the codec has it. Yes, it has. So this is a rendering of the real universe. The whole movie you can play if you want. This is our real local universe, cosmic web, on the basis of the flow pattern in the cosmic web. Isn't it beautiful? Thank you very much.
So now is time for questions. Yeah.
I have one question. Can you open, please, the slide with the angular two-point correlation function? It was at the start of the presentation.
Okay, let me stop this one. Let me... You mean this one?
It was...
This one?
No, it was the long function.
Oh, the
Yeah,
Limber,
yeah.
the Limber equation.
Yeah,
This
yeah,
one.
yeah.
Yeah.
Can you? I cannot see the angular dependencies on the.
So
right
this is the angular
function.
two-point correlation function. This is the spatial one, and here you see basically the projection from two elements on the sky, right? So you have the projection along that, and you have the projection for that one. So this is a double integral, and this is basically the radial selection function that is coming in. So how many galaxies you're projecting on there.
Yeah, I understand. Probably I have some problems with math, but I don't see any function that is dependent. I don't see any function that depends from
On depth.
angle on the right side.
I think.
Yeah.
Oh,
Yeah.
oh. So what this is basically this is a location and this is a location, like along that line of sight and then along that side of sight. And actually this integral is constrained along, if you take it along those that angle, that's the angle theta, you're constrained to integrate along that side and along that line of sight that are separate by an angle theta.
Okay.
Right? So it's not a total integral, it's a constraint integral.
The integral over two cylinders.
Yeah.
Thank you.
So
Two
mathematically
cones.
speaking,
Two
it's
cones.
in the
Yeah.
so value in the correlation function. You need some variable transformation. You can do that.
Yeah.
Yeah.
It was an infamous exam question for cosmology.
May I ask also a question?
Yes.
Now, it is beautiful. I mean, you can determine, assuming going on, all these parameters for different points. Then you can take a cube and have all your parameters, all of them very with some noise. And then you make the cube larger and larger, and then you do the same in different positions. At some point, you should reach a point, the universe probably is large enough, where all these parameters are the same in different cubes within the noise that is cosmic noise. Are you able to do that already? Did you do it, or
We didn't do it systematically, but we have been applying, for example, Nexus on various Virgo simulations. So there is now a very large one, a box of more than 500 megaparsecs, pp millennium. And then we just look at it with Millennium 2. And both of them should contain sort of the same structure. And you see that indeed the Millennium 2 is a little bit on the short side in terms of the filaments, but it's getting there. So you are sort of approaching, in the PP millennium, you don't find larger structures anymore. They're slightly larger, but not comparable to the box.
So you finally are able to have a characteristic.
Yeah, and you can understand why, because this cosmic web is there on a scale where you basically are dynamically in between linear and getting towards nonlinear. Halfway in, basically the Zeldovich scale. So that is around 100 to 200 megaparsecs. Beyond that, you don't see filaments anymore. It's on the way of becoming, but it will never do because lambda is pushing the things aside. So you can't pick them up.
Any other questions? Yes.
Well, a question about linear here when you showed one black arm and red one. It's about the empty space between these two arms. Isn't it a void?
Yeah, it's a void. There is a huge void between us and Piscis Perseus.
Is it possible that this void will be expanding faster than these two arms?
That's an interesting question, but the answer is probably not. In the sense of, you have to be very careful in stating the answer. If you would measure the velocities of the galaxies here, imagine that you would be able to do it as accurate as Brent was able to do it for the local void. We cannot, it's too far away, but imagine. Then you would indeed find that the galaxies here are pushed against this local supercluster, right? You see here also local void. So in a sense, close to home, that's what we found. Right? We are around here. Same for Piscis Perseus. But overall, the fact that they found this Laniakea thing, and that's the next one, means, and Laniakea is basically identified as the gravitationally bound structure. That means that structure is not really expanding anymore. So the void is compensated basically by the overdense structures around it. And that means that on the other side of of those structures, you don't feel that void anymore because it's compensated by the overdensities that come in between. Right? That gravitationally bound structure does no longer expand because of the void. Right? That answers your question?
I think yes.
Okay.
Any other question or comment?
I think everyone is out for coffee.
Yeah. Then let's then